Good morning. If you found yourself in the hydro session this morning, starting at 11, you're in the right spot. We have three presenters that will be talking about some of their research and their work. The first is Noah Irby from Houston Engineering Incorporated. The title of his talk is Improving Data Over Time, a discussion on strengthening analysis with improved methods using NEXRAD Rainfall processing for HEC-HMS Hydrologic modeling. You can go ahead and share your screen, Noah.
Sure. Are we sharing video too?
If you want, you don't have to.
Oh, I would love to. All right, let me know when you can see everything here.
That looks great.
All right, well, thank you everyone for coming today. Like I said, my name is Noah Irby from Houston, and my presentation's on improving data over time. So bear with me, it's my first time doing a virtual kind of conference here, so it might be a little rough around the edges, but I think we're gonna have some fun today. So strengthening analyses with improved methods using NEXRAD rainfall processing for HEC-HMS hydrologic modeling. If my slide will change there. All right, so just a quick introduction. Who am I, what is NEXRAD, and what is HEC-HMS? So I'm a GIS analyst, as I assume approximately, my slides are kind of slow here, 25% of all geospatial professionals in the US are. Some of you perhaps even in the audience today. Specifically, I do a lot of work with weather, hydrological, transportation, scientific programming, and environmental applications. NEXRAD, here I've got a picture of an umbrella. I want you to think about rain, right? So next generation weather radar. It monitors precipitation and atmospheric movement. But today we'll mostly be looking at the rain stuff. And HEC-HMS, which is the US Army Corps of Engineers Hydrologic Engineering Center Hydrologic Modeling System. That's kind of a mouthful, so we just call it HEC-HMS. There you go, simulates complete hydrologic processes of watershed systems. So NEXRAD coverage. So this NEXRAD system, here's just a quick diagram showing where all the coverage areas are within the contiguous United States. You can see it's pretty good coverage. Like there's a little bit of a gap here in like Nevada, that kind of area. And then up here in this very north part of Minnesota. But generally speaking, we're gonna have pretty good coverage all around the United States. And then also up here in Alaska, Hawaii, even South Korea. So pretty much just a contiguous weather system. So what do we use NEXRAD data for specifically? So it's a real world historical data source for estimated precipitation that does not rely on the presence of a rain gauge within a study area. So you can do exceedingly rural watersheds and things like that where there may not be as many data points available for local data. It offers outstanding temporal resolution between 5 minutes and 10 minutes. It's just a scan every 5 minutes or so. And is available relatively quickly after a storm event. Now, about after 72 hours, there'll be some NEXRAD data. Abstracting this to something our engineers can use in HEC-HMS allows us to produce a runoff hydrograph, which is going to show us how much water accumulates where and how quickly it dissipates, rainfall for effect, produce floodplain polygons, determine the downstream benefits or impact of a practice. So specifically with what we do, a lot of the time has to do with flooding and reducing flooding impacts to both structures and crops and things like that. And then here's just a quick diagram showing some of the components of runoff, precipitation being what we're using the NEXRAD for. But the modeling itself is going to include things like the soils and the slope and LiDAR and things like that. So what does this data look like? I've got a quick video here to share of some of this NEXRAD data. Let me just give it a second here to load. And then once it thinks about it, we'll see some cool rainfall. Okay, so this is like the Grand Forks Weather Station, and this is kind of the generalized coverage area. And you can see this sort of rain coming in, the intensity as it goes up to right here. And then our study area for this specific one that we did, Park River Basin, and specifically the North Branch Park River Basin. But it's just kind of cool to see like a a generalized idea, and the hours counting up in the top left. So each of these frames is 1 hour increment of the actual rainfall in inches per hour. So zooming into our study area, we see some of the hydrography and hydrology aspects, and then the subbasins, just kind of the local characteristics of the area. But this is the really cool part, right? So we plug all this into the model, and then we can, oh, must have accidentally paused it there. We can see like where the water is building up, how much is accumulating, and then how much is like shedding off the landscape and going downstream. I think it's kind of a neat thing to see. You can see how deep it is and how long it's going to stay there. And really helps us to determine like what kind of impacts are going to happen and where. And then we can plug things like, all right, what if we want to add a dam rehabilitation into our model, see how that affects the flow, things like that. How's that going to change? What people are affected and where? Now, sorry about these slide transitions, guys. They're kind of, I don't know if the connection's great or what. There you go. So what kind of work does this support? One example is evaluate dam performance, design, and safety. So like I was saying, if we see a dam that we don't think is performing acceptably, we might go out and study it and see like what kind of improvements we can make, how that might affect the flow, things like that. Evaluate downstream risks to structures, cropland, et cetera, and then supplement sedimentation, water quality analysis, environmental impacts. So here's just another quick graphic of showing like a dam breach event. So what were to happen if a dam were to fail, or if the water were to exceed the level that the dam can safely support. You can see kind of like a backflow coming, and then that concentration of water moving downstream, and all those green and black dots are structures, and you can see like what kind of risk is involved, what kind of damages might you expect, things like that. And I just think it's kind of a cool thing to show, because at the end it just kind of goes everywhere, right? And then there's just some of our sediment load, things like that for water quality. All these things we can help, our models can help us kind of figure out. So what were the problems, right? So we have all this data, we're doing these cool stuff, right? But what were the problems? It was good enough, but the workflow was complicated. We had 5 individual scripts with many inputs to keep track of across them, and the data acquisition and manual pre-processing steps were cumbersome and slow. Data quality. So at the time that the tools were developed, before I came to the company, the data utilized was the best available. So I don't fault anyone there. It was the digital precipitation array, using instantaneous measurement of estimated 1 hour precipitation accumulation. You heard that right. It's both an instantaneous measurement of an estimate and like over a quantity of time, but they're at that 5 to 10 minute interval. So you had to end up doing like some kind of interpolation between them to get an actual 1 hour increment precipitation amount, as opposed to just getting like a rate or something. And even just saying that, all I can think is that's kind of whack. But since then, NEXRAD has expanded the capabilities of their sensors, adding dual polarization. This allowed for a new data product, the digital precipitation rate, which is an instantaneous measurement of that precipitation rate. So instead of doing this complicated back conversion, it's just like, all right, for this, from this data step to this data step, this is how much rain is falling, the rate at which it's flowing. So, and our third problem, there's no available budget or time to make improvements. So time, budget. So what makes the new data better? We'll just kind of compare and contrast the digital precipitation array and the digital precipitation rate. One thing is this dual polarization, which adds vertical pulses and allows for more accurate data collection. So here's a cool graphic that I jacked from Wikipedia, which is a great source, by the way, showing non-polarimetric radar versus polarimetric radar. So on the left, you can see it's transmitting and receiving just those horizontal pulses. One on the right, it's got the horizontals and the verticals. And here's kind of a more static graphic showing that as well, with the horizontal in the blue and then the vertical in that sort of purplish red, which gives sort of a cross section and not just a pulse, right? Which helps you to determine what kind of hydrometeor it may be, whether snow, hail, or rain, and also a better estimate of the rate. And I'm not really a scientific paper guy, but if you have any interest in this stuff at all, this is actually a pretty cool paper that I would suggest checking out. So DPA versus DPR. So the digital precipitation array, the old stuff, was a 4.7625 kilometer gridded resolution data product with an estimate of 1 hour accumulation based on that non-polarimetric radar, requiring that back conversion to the rate due to the workflow, WAC, and this significantly increased process load because it's not just as simple as applying like a number to convert it, like converting meter to feet. It's like converting between a couple different data formats. Digital precipitation rate, or DPR, much finer variable resolution based partially on the distance from the sensor. And this is a cool graphic that I totally didn't add last second, which shows the DPA in red, this big 4.7625 kilometer grid versus this DPR. You can see there's about 50 of them in there. And so one of the advantages of this is if you have, say, one erroneous data point or one outlier, there's enough data points around it that is not going to impact the results significantly. Whereas with this digital precipitation array, if one of them's off, then you could have significantly different results for watershed, especially smaller watersheds. So anywhere from 10 times to 50 times better than the digital precipitation array. And it's, again, the instantaneous rate of precipitation in inches per hour, which is a much more friendly thing to work with when you want the full accumulation, eliminating that conversion step. So let's just talk a little bit about the data abstraction here. I like to think of data abstraction as going from point A to point B. In this case, point A being the raw NEXRAD data product, and point B being the end use product for HEC-HMS. Whenever I do any kind of data abstraction, I start typically from point B and work my way backwards. I want to know exactly what the constraints are on the output that I need to provide are. And so in this case, it needed to be simplified to a 1 hour time step. So saying like in the first hour, there's this much precipitation, in the second hour, there's this much, and so forth. Aligned to the HEC-HMS SHG grid, which is just a standardized grid cell used by US Army Corps. So just another layer of abstraction there. And then using the proprietary HEC DSS file format, which thankfully the US Army Corps provides a script for conversion of ASCII text file to DSS in this instance. So here's a flag on a map representing we're going back to point A. In case, to make that as efficient as possible, we need to acquire the data effectively and then design a workflow to cover the distance from A to B. So I won't get too into the nuts and bolts here, but I will kind of compare and contrast the old process versus the new process using popular meme template, board poo versus fancy poo, right? So the old workflow had a manually download and pre-process data, convert to shapefile for use in ArcGIS using NOA Weather and Climate Toolkit, a script to create summary tables from calibration data with 13 parameters, a script to convert accumulation to summarized table with 4 parameters, a script to combine tables to a single formatted table with 10 parameters, a script to convert a formatted table to ASCII grids with 3 parameters, and then a script to convert ASCII grids to output DSS format with 10 parameters. All that adds up to an arduous manual acquisition, 5 scripts and 40 parameters. I don't know if you could tell, but while I was reading that, board poo looked like you got even more bored, right? Fancy poo, on the other hand, the new workflow, revised the download and pre-processing, saving 50% of the time as before, simplified it down to 1 script with 9 parameters. Now that's, dare I say, pretty fancy. So how do we solve the issues? And this can apply more to other problems in GIS as well, not just specifically HEC-HMS modeling. This is just more generalized, right? Seek to understand the data and the problem on a deeper level. So before I got here, when I got here, they give me this script and they show me how to use it. And they're just like, all right, this is the process we need to do sometimes. But that's not, I can't be content with that, right? I got to understand what I'm actually doing. What are the inputs? What are the outputs? What is the output used for? How's the process actually working? Can you achieve the same end with different inputs? Don't be afraid to go into the workflow, see what it's doing and how it works, even if you're unfamiliar with it, right? Open up that Python script. Everyone starts somewhere and Google is your best friend. I can't tell you how many times I've been able to just be like, Google like the expression that I'm trying to figure out. And then some user out there has done something similar that I can adapt, right? Whether it's Python or JavaScript or C# or whatever language you're using, there's so many million daily active users that someone out there has likely done something similar that you can learn from. And then also just keep up to date with developments in software and industry, which everyone here is doing today just by virtue of attending this conference, right? So for example, the improvements to the download process were only possible because of a recent update to the Weather and Climate Toolkit. If I hadn't been following what NOAA's doing and what kind of improvements they're making to their software, I might not have known that, hey, we're integrating Amazon Web Services so you can download data about 10 times faster, right? And then how do we solve the no timer budget, right? We'll do the math. Start with an outline. How much time and headache you think you can save versus the time needed to improve the process? In our case, I created a budget for 20 hours of coding work, estimated it would cut our process time in the long run from 2 hours to about 15 minutes. So investing that 20 hours up front pays off after using it for just 12 runs. That's a lot more palatable than just saying, hey, I need 20 hours to fix this stuff, right? Being able to not only put it in terms of like the payoff, but also communicating effectively what the issue is, like how this is affecting the data and how it could be better to that project manager or to that person that approves things, right? Whoever that is. That's going to be really helpful. And then don't be afraid to automate, right? So I know there's a lot of talk, at least I hear in our industry, of, oh, we're automating ourselves out of a job and robots and algorithms are going to replace us. Well, that's true. Process improvements are not the enemy, and robots and algorithms will replace us all eventually, especially if this guy has anything to do with it. But creating the robots might help you stick around a little longer. So just extending this discussion, the moral of the story, don't be content with good enough. Just because a process is working and it's good enough and fulfills the needs of your organization doesn't mean you can't improve it. Develop a technological ethos. Maybe it's not even the same as mine. So the one I'm talking about today, don't be content with good enough, right? But whatever those practices or values that distinguish you, your organization, or society from others, develop that. Learn what those things are, right? Embrace them. Can we apply those to other areas in our work, right? So say, for example, you're a county GIS administrator and you got to be in charge of everything from soils, parcels, wetlands, utilities, survey processes, right? Like what things are you doing right now that are good enough that you could improve on? Can we apply this ethos to other areas in our lives? Am I a good enough husband, wife, brother, mentor? Are there new developments in research, technology, or our personal lifestyle that can help us be more than good enough? For example, all this improvement in Zoom and like Facebook Messenger, like these video platforms, I've been able to connect with extended family members, right? And be a better cousin, for instance. The point is not to second guess every single process or decision we make, but develop a technological ethos that helps us make better decisions in the first place. So just to summarize, good enough is tired. I don't want to hear that. Push the standard for your organization, even if it brings you outside of your comfort zone, even if you have to Google something, right? And push the standard for yourself, especially if it brings you outside of your comfort zone. And that's about all I've got.
What in the world is going on?
I'm sorry?
Can you hear me, Noah?
Yep, you're coming through, Kate.
You know.
I've seemed to lost, my Zoom is kind of flaking out here. Can you hear me now?
Yep.
Oh, strange. Okay, sorry about that. I still can't quite see the screen. I'll figure that out later. But wow, thanks for that great presentation. You made some really great improvements to your workflow and some great advice on how you got there. I just really like that a lot. If anyone has any questions, you can put them up in the Q&A or in the chat. And we have quite a bit of time for questions for Noah. And I guess my question to you is, how often do you run the model, or what, you showed us the example of that watershed that you're working on in North Dakota with the dam failure example. But what other reasons or what other things you use this model for? Just out of curiosity from someone who's not in hydro.
Well, specifically the work that I do with the engineers in my company, we do a lot of like dam improvements and dam replacements and things like that. Could be like ditch rehabilitations. Outside of those specific aspects of like watershed management, I don't know what it's used for. We just happen to have enough of that it keeps me busy.
Okay.
But I mean, you could use it for anything from urban stormwater management to like, I don't know, just your own land, like just wanting to figure out where water is going. I guess I just, outside of the applications I listed, I don't have that much experience with what it could be used for.
Mm-hmm.
There's all kinds of other like actual parameters with the NEXRAD data that you could do things with though, like different characteristics of the atmosphere, how much wind is going, things like that. But I'm not super familiar with those. So.
And one other question, what is a .dss file? I haven't heard of that file type.
Oh, so that's just, it's basically just a fancy text file that the only reason it's a DSS file is because the Army Corps of Engineers wants it to be proprietary. That's my understanding.
Okay.
Like actually dissect it. It's not that much different than just a complicated text file. I see a question in the Q&A. Is the NEXRAD corrected at all with rain gauge data? It is when there's rain gauge data available. And that was specifically something that was relied on a lot for the old process. It's still calibrated or corrected with the new process as well. It's just not as significant of a factor. So where it's available, but sometimes there's not a good rain gauge nearby, you know, and the process for that would be something like interpolating the actual values across and then correcting through. But that's kind of boring. So.
I'm not sure. Kate might be having some issues with her Zoom meeting here. We'll give her a minute to get reconnected.
Okay, sorry about that. I think I'm back. Zoom froze on me.
We can hear you, Kate.
Thank you. So I just wanted to say before I realized no one could hear me that I really liked how Noah mentioned keeping up with the software and the industry changes. You know, that's imperative in our work, isn't it? Things change so frequently, programming languages and the ways we access data. So that's really great advice. I really enjoyed your presentation. So if there's any other questions, we can take them. Otherwise, we'll start the next presentation at 11:30. Hello, everyone. So we're in session 20, the hydro session, and we're ready for our second presenter. Jennifer Ward will be presenting a video by Lange of Pro West and Associates. The title of their talk is "It Started with One Map: How We Built a Complete Drainage Management System Using GIS."
Thanks, Kate. This is Jen Ward with Pro West. And as Kate stated, I'm going to be introducing Lange, who pre-recorded the presentation due to scheduling conflicts. And the presentation that Alex is going to be focusing on is dealing with drainage. And as we all know, here in Minnesota, drainage is a big deal for a lot of our counties. And what Alex is going to be going over is how Renville County specifically was able to build a comprehensive GIS system that not only enhanced their workflow, but also allowed them to become a lot more efficient with their tasks, their daily tasks that dealt with drainage systems and inventory and things of that nature. So with that being said, let me go ahead and share my screen here. Bear with me here 1 second. It was all so smooth during the practice, right, Kate?
It usually is, right? That looks great.
All right, and then let me make sure that I'm sharing the audio because we learned that that was an issue here this morning. Let's see. Share sound is checked. All right, here we go.
Hi, everyone, and welcome to It Started with One Map: Building a Complete Drainage Management System with GIS. My name is Alex Lange, a Solutions Engineer with Pro West and Associates. Sorry I can't give you this presentation live on a webinar, but with scheduling conflicts, we weren't able to get that done. But Jennifer Ward is on the call with us today, and she'll be able to answer any of your questions. Or if she can't, she'll relay those to me, and we'll get you those answers as soon as possible. So we're talking about drainage management systems today. And this is a project that's pretty close to me because the project actually started back when I was the GIS specialist for Renville County, where the drainage system that we're talking about today hails from. And worked on this project as a GIS specialist, and then as I transitioned over to Pro West, I still work on it with them in a partnership. So it's a project pretty close to me, and I hope you guys are gonna like it as well. So Renville County is a small rural county in Minnesota. Only 10 small cities instead of one larger city with smaller towns. So it's a little bit unique in that respect. But we have 150 plus unique drainage systems that we have to manage. You know, as you can see on the screen, approximately 770 miles of open ditch channel, which nearly 1,400 of drainage tile. So it's a large system that only 3 staff actually manage at the county. So turning to GIS to make this system more efficient and usable is very key. And so what Renville County decided to do was start with the basics. But what did they have to start with? So back in 2018, Renville Drainage had one web map that they used for ArcGIS Collector. They had a third-party system for tracking repairs and had no access to actually edit drainage information. At the time, there was only a layer for open drainage ditches and open drainage tile, and those were not able to actually be edited by drainage staff. They also were right in the midst of a process called redetermination, and we'll get into that a little bit later. But know that redetermination is a process for redetermining benefits of a drainage system for those a part of a given area. Now we start as we start with any GIS project, Renville County started with their data. So we see that the drainage data, in this case, the open ditches and drainage tile, we're going to update the schema, add new attributes, and clean everything up so that we have a nice foundation in order to build that data off of. Because without data, we don't have GIS. So it's very key in order to, if you're going to improve the system, start with that good base. And so we start with those open ditches and tile lines, and we also improved the tile improvement layer, which is a layer that Renville County uses to track new tile lines or to update existing ones to better match what's on the ground on the system. And then we start getting into the new development. So a few years ago, there was a new law that came into place that says that every drainage system has to be inspected every 5 years. Now, with small staff, the easiest way to do that was to create a paper form, go out, fill in the various check boxes, and submit that to county commissioners at the end of each year. But because we were developing this really nice GIS system, Renville County decided to leverage ArcGIS Survey 123 to actually perform these given inspections. You can see all of the different aspects and different attributes that were collected during these inspections. But the key pieces to look at here is required and completed repairs. So for the first time, Renville County was now tracking repairs that they noted out in the fields while they were doing these inspections, actually noting these repairs before they were presented to them, and actually tracking them with a feature class, and tracking any existing repairs that had already happened with tabular data. All these compile into this one inspection form, which actually populates 5 separate GIS layers, those required and completed repairs. And we're also collecting line data to track buffer compliance, noxious weeds, and trees. So noxious weed and trees have to be removed. And buffer compliance is also another law that drainage systems have to adhere to, where 16.5 feet around every open ditch has to be seeded with grass. So we're tracking all of this through one inspection form. So the first time we're digitizing what normally would have been a paper system for the small staff. Integration. So we're going to integrate this GIS system. The best way to do that is through some sort of reporting system. We have this data on all these really great inspections, so it's really good to be able to integrate with forms, such that the county had an ArcGIS enterprise system that they could then bring that GIS data into a form via a nightly process. So whenever these inspections are completed, they can be printed off and given to various staff members to track what has been collected during a given inspection. And so since this is on a 5-year rotation, we've begun to create not only a record in the GIS system, but also a paper record that can be used for formal looks back at what was found during any given inspection day. Expansion. So we're going to expand this GIS system. We've already now utilized Survey 123, adding these new layers in there, but now we're also getting development on several sides of the coin. So new staff was hired with GIS experience, which now gives us the opportunity to give access, or Renville County can give access to drainage staff through web GIS systems. So utilizing that ArcGIS Enterprise portal and ArcGIS Online, we're able to actually publish data out and give them edit access to their existing data to add or update attribute or location-based information. We also developed the very first new web GIS solution for Renville County, which was the drainage editor, taking all those data layers and packing it into a smart editor widget enabled tool so that they can edit the attribute and location data of their drainage systems. And then we can bring in new data. Because we have staff that is now being trained on GIS, we can bring in new layers and new assets that want to be tracked for Renville's drainage operations. A new layer was developed for county crossings, meaning where an open ditch is being crossed by, say, a road or a field crossing. We're marking those and what type of culvert is underneath those. Camera jobs, so the county is able to track all of the places where it has run a camera through tile lines. And tile line construction, whenever there's new data that's coming in, we want to track the year and some other attributes about who's performing those tile line constructions before we bring them into the formal tile line layer. Redeterminations. So redeterminations is a fairly complex process that actually is a multi-year endeavor for any drainage system in Minnesota. So these original benefit amounts. So the drainage ditch has a certain amount of benefit to its given farmers in this case. And we track those benefits via a dollar amount or the benefit that they're getting from that system. Now, because these are law, once they're signed into law, they cannot be changed unless they go through a process of redetermination. And most of Renville County's drainage ditches had not been redetermined since the early 50s or late 40s. So this was a process that was well overdue, and a process that Renville County was excited to get going to get these numbers up to date. But through that process, more GIS data was able to be collected as part of the redetermination process. Not only can GIS help them help them as far as bringing in GIS layers to make sure these redetermination boundaries and the systems match up correctly, but we actually get some product from that from those redetermination layers. So through this, we were able to come up with another new web application that actually takes a look at those benefit amounts. So using the tax database, integrating with the tax database and creating an automatic download of that data with the parcels, we're able to actually display what benefit information is going on in all of the Renville County systems based on the tax data. And pulling this all into this web application, now the county staff is able to select a given drainage ditch and pull up all the information on the entire system, or they can select a given parcel and come up with the benefits that are on that particular landowner or a requirement of that given landowner. This is very, very good stuff because now it's not only something that the auditor, treasurer, or the assessors get to look at, but something that can be shared with the drainage staff or any staff that may get a question about benefit amounts. So when the public calls in, we're able to actually pull up this web application and get that information right away. Continuing on with this process of automation, we're also bringing in that benefit information from the redeterminations. So because of the redeterminations, they get to classify the land that that is part of the drainage system. And through that classification, we get that dollar amount, that new benefit amount per land class, and we get these beautiful land class files along with them. So using that land class data with a little bit of ArcGIS Pro and a little bit of publishing, we're able to pull that layer into a web-based system so that not only can we see benefit information based on actual GIS calculations, we can also get up-to-date information when parcel land splits happen. So this process will run, a parcel is split, and we get new benefit information that can be entered into the tax system rather than just viewed. So you can think of this as the other side of the coin to what we were just looking at, the benefit amounts before they actually get entered into the tax data. And then the big one that was a long time coming for Renville County, since they started to track repairs in the system due to those inspections. The thought was, well, let's take this the whole way. So Renville County decided to start tracking all repairs with the ArcGIS Enterprise system. So we've developed a repair maintenance tracking application that's able to bring together all the repair layers into one distinct application, so that when repairs are called in from the public or they're learned of through other ways, the Renville County drainage staff can come in, add the repairs, and start tracking the statuses across the board as these repairs are repaired, and whether they're invoiced and brought into the system. And speaking of invoices, we weren't done with integration just yet. Because we want to track the repairs and track historical records, we have two integrations with these repairs. The first is Renville County's document management system. So any document that they would like to attach to any given repair along the way can be put into their management system, and through a unique identifier, able to link to the GIS points. So as soon as you click on one of those icons or given repairs within the web application, you can pull up a listing of all the documents that have been attached to that given area. And then the other integration is yet another report similar to the inspection reports, but this time we're doing a system-wide. So an entire drainage system is being brought together into one report. So anything collected during an inspection or anything added via the web application tool is brought into one cumulative centralized report to list out and show all that's happening on a given system. These are great summary documents that can be referred to by county staff or county commissioners. So I know I went through everything very quick, but let's recap exactly everything that was done over this period for Renville drainage. We updated data schemas. We updated their mobile capabilities. We updated and added new ditch inspection forms via Survey 123, new web applications to better track and manage existing data as well as add new data. We have new application to better look at ditch benefit information, as well as creating new ditch benefit information and entering into the system utilizing those land classification files. And then finally, it sits all together with a very integrated application for repair maintenance tracking to see all of those given attached to documents, bring together all the repairs into one particular report. Really, when it comes down to it, there isn't a workflow that Renville County Drainage has put together that doesn't touch GIS now. And it's proving that GIS can be really great at making your systems efficient, but also improving operations across the board. This is something where the Renville County Drainage is extremely thankful for GIS and are continually thinking of new ways to add new applications or new data into their overall system. I hope you guys have enjoyed listening about it, and certainly Renville is very happy to bring that to you. So a special thanks for them for allowing me to talk about this, and hope everybody has a great rest of your conference. And back to you, Jen.
All right. So hello again, everybody. So this is Jen Ward with ProWest again. I'm not sure if there's any questions that anybody has. I can try my best to answer them. And believe it or not, a lot of them I probably can. But anything that I'm not able to answer, we can certainly make sure to capture those questions and then have Alex get back to you directly when he's back in the office next week.
Yeah, as Jen said, you could put your questions up in the Q&A window or the chat. And thanks to Jen for showing this, and Alex for recording, and Bill for allowing us to see the work that he was able to perform for them.
Yeah, and tracking. Special shout out to Renville County too, because it's always a great thing when an organization, they may not be too happy about the idea of doing the presenting themselves, but the fact that we're able to show what they're doing is, I think, such a huge benefit.
Yeah, and I think the model that he put together for tracking, monitoring, repairing, it's all one comprehensive way to track drainage throughout the county. It's an impressive piece of work. I'm really glad they shared that. So I have a question. So now that it's all been built, who's maintaining the products? Is that something that ProWest does, or is that put onto the GIS staff at Renville?
So the majority of the day-to-day stuff is maintained by the GS specialist at Renville County now. So we went through some training sessions with that individual, got him up to speed. So they're doing the maintenance internally. And then if there's like additional functionalities or things that pop up, then they just contact us. And when I say us, I basically mean Alex, right? To help assist with maybe some questions or additional things they'd like to add. But really the goal with Renville and them having the full enterprise system in place there is for them to become as self-sufficient as possible, utilizing, the ability to integrate all those variety of systems that Alex was talking about, and to really make the most of it for not only internal usage, but also for internal maintenance.
Absolutely.
All right, well, thanks so much, Kate.
Yeah, thank you, Jen. And make sure to thank Alex for us. And thanks for all the folks here listening in. The next presentation will begin on the hour. So we have about 9 minutes, and we'll resume with our next presenter, who is Tyler Kybish. And I'll tell you more about that in a few minutes. Thank you. Hello, everyone. Welcome back. We are ready for our third presenter in session 20, Hydro. Our third presenter is Tyler Kabish of Ayers Associates. The title of his talk is Deriving Hydrography from LIDAR.
All right. Thank you so much. Let me get set up here. All right. Is everybody able to see my screen?
Yeah, that looks good, Tyler.
Great. Wonderful. All right. Well, we will dive right in. Today, I'm going to be talking to you about deriving hydrography from LIDAR products. And my name is Tyler Kabish, and I'm a geospatial project manager with Ayers Associates. We are based out of Wisconsin. We have offices in Eau Claire and Madison, and I'm based in Waukesha. But some of my history, I actually used to be located in Minnesota. I used to work for the Minnesota DNR up in the remote sensing lab maybe about 7 years ago or so. So very familiar with the Minnesota landscape. Oops, there we go. Okay, so let's dive right in and just start talking about hydrography. So is hydrography data really that important? Who uses it? Why is it good to keep up to date? And really, over the last few decades, we've been doing some hydrography studies just to see how important it is. And really, the benefits study has analyzed it and said they can put a dollar value on this and say that there's about $538 million in annual benefits that the current hydrography program provides. Just having that data and being able to utilize that data for other management strategies or best management practices. And now moving forward into the 3D enabled world, we can see that a 3D hydrography program, they could provide almost 2 to 3 times the benefit, $1.14 billion in annual benefits, if the hydrography data was just that more accurate. And different agencies across the state and federal and local districts can all benefit. Soil and water districts, flood mitigation, wildlife managers, national resource managers, and obviously state and county partners. So utilizing LIDAR to derive the hydrography really came about because the current NHD or the 24K stream and river centerline inventories are a little bit out of date. Typically, these hydrography inventories stem from the 1960s USGS topo quad maps, and those were hand drawn from aerial imagery, from the time, and they may have been accurate in areas where there was not canopy coverage, so in farm fields or open terrain, the streamlines may have been very accurate back in the 60s. However, since that time, different rain events across the landscape have changed how rivers or where rivers are flowing. And then since we have LIDAR, we can see through that canopy and actually get an accurate surface model to depict where the true flow of water is. And again, I just want to drive that point home, is that we're trying to replicate the true flow of concentrated water across the landscape. Where is it actually flowing when that raindrop hits the surface? And so here we have a few examples of a LIDAR DEM. On the lower left, we have a LIDAR DEM and then a hydro and forest LIDAR DEM. So we can see that there's like a two-lane freeway or highway, and then a railroad track just to the south of that. And then what we've done is we've done an inventory on the culvert locations, and we've incorporated those and burned those into the DEM and created a hydro modified DEM. So then we can use this DEM to create hydro products and processing to derive a stream network. So the water would actually flow through the culverts. And if you don't incorporate this step and try to run a stream analysis across the DEM, the water will start ponding on the uphill side of any digital dam. So any road that there should be a culvert for, or if there's a bridge or an actual hydro dam across the landscape. And then this image in the lower right is an example of an HPI, which is another LiDAR derived product. It's a hydrologic position index. And really what this is designed to do is to show the user's eye a little bit more where the concave and convex surfaces are across the landscape. So it's very similar to a DEM, but it really makes the concave convex structures along a river or a riparian area pop out to the user's eyes. So we can, as users, we can readily see where the stream channels are in this red HPI image. And here's that same image. And again, we can see quite a bit of detail. You know, even in the southern reaches, we can see those meander bends really well with this product. And so again, what we want to highlight is that the current inventories that are out there for stream and river center lines, they don't accurately present the hydrography well. They don't encompass all of the hydrography features, and they just don't go to the detail that we have the data available for today. And so what we can do is incorporate the LiDAR, create hydraulic models, and update those line networks to provide much more detail for every meander bend. And in turn, that will actually increase the overall length of your stream miles. So that may be benefit for many, that may be of benefit for many different best management practices or wildlife management strategies. So we can update the current inventories, but we can also go a step further and we can incorporate other hydrologic features that haven't been in previous inventories. And so what we're seeing here is an extended network of the water conveyance features out there on the landscape. And this is kind of a raw product. This is an intermediate step. So there may be the need to incorporate some more culverts along the landscape, or refocus your efforts on which streams you really want to incorporate in the final products at this point. The main methods for accomplishing these tasks are collecting those culvert inventories and applying the culvert inventory to your LiDAR, your current LiDAR DEMs to create that hydro modified DEM. Now you can do this in multiple different software packages, one of which just happens to be ArcHydro. You can download ArcHydro and incorporate that into your ArcPro or ArcMap desktop version. I believe currently there's over 350 tools in the ArcHydro package. So there's many different avenues you can explore. For these methods, it's been widely documented in various scientific papers that, you know, in order to complete a stream analysis, you would like to do a flow direction, a contributing area, and a stream definition by threshold. And you can play with those thresholds to get your various detailed outputs, but this is the main method for calculating updated hydrography. So here we have an example of a county in Wisconsin where we've inventoried all of the culverts across the county. So this is about 15,572 culverts across this county. And you can kind of see there's a grid, right? A lot of these culverts are going along county roads and then on any other major roads leading in and out of urban areas. So for this one, that was an average of 49 culverts per square mile. That's kind of a lot. There may be fewer of those if you don't have urban environments or as much subdivision. If there's just a lot more farm fields, you may have less culverts than that. But so this is one of your main inputs. Here we have on the upper left, we have a DEM and then our line inventory of our culverts overlaid. And then on the upper right, we can see that same area with the aerial imagery. So we can see that our culvert lines are overlapping with some field approaches to some farms, maybe an approach to a hunting stand, and then there's a culvert in the middle going through the road for this drainage. Then in the center bottom of my screen here, you can see that here's that hydrography line that we've derived, going through that culvert. And this is this hydrography is replicating the 24K. So if we were to go very detailed, we would be able to see the lines flowing through the culverts on the field approaches, but those aren't necessarily perennial streams that have water flowing in them all year. So for this purpose, we're just trying to replicate that or update the 24K or the NHD hydrography lines. Here we have some more 3D examples of the hydrography flowing through the 3D culvert lines. And so what happens actually is the 3D culvert line gets draped onto the DEM surface. And so the culvert actually has an uphill elevation and a downhill downside elevation associated with that. So it actually is slightly tilted. I don't know if you can really see that in this image, but the culvert does have an elevation associated with it. So we know that the water will flow in and out of that line. Here's another example, and you can see that, right, it's actually cut, it's actually inside of the road. So it's not like the stream has been draped over the road or flowing over the road, it's flowing through the road where that culvert should actually be on the ground. And this is just one more of those images where you can see it's actually cut through the road and draped to the surface elevation for where that water is flowing. These 3D images really depict that well. So here we have that same culvert data set from Calumet County in Wisconsin. And then we've picked a HEC-12 watershed, or I believe this is a HEC-10 watershed in the middle of that county. And so we've clipped out the DEM with a little bit of a buffer around that. And then we have our culverts on top of that. And then we're going to run our hydro processes over this to derive a stream network. Now here's an example of that stream network with the DEM colorized with red for the higher elevation and blue for the lower elevation. You can see that there are headwater streams, and then they're coming down to meet in the bottom of this HEC-12 or HEC-10, sorry. Here's that same watershed, and we just have this overlaid with all of our culvert lines on there. So the watershed is, the hydrography is in blue, and then the culverts are in black. And obviously you can see, right, the culvert lines are following the county lines, right? They're basically every farm approach, every driveway is inventoried within this. And then the reason here up in the headwaters, we see some streams flowing out of the watershed is we like to run a buffer on the watershed to make sure that, first off, that the watershed polygon is actually correct. And then to see if any water is accounted for within this watershed that should be flowing somewhere else. So here we have a stream in the very northern part of the headwater that maybe this part of the watershed should be allocated to the watershed north. So maybe this watershed polygon should be updated as well. And really, you don't know these things until you explore the methods and you create some products, and it's an iterative process. You may need to go back to the beginning and start all over again with some new data sets, but along the way, you'll come out with some really detailed products. Here again, we have some more examples of the hydrography incorporated with hydro break lines from water bodies. We have the culverts in black along the roads and some driveways. Where the streams are overlaying the roads, the streams are overlaid on top of the culverts. So it's hard to see the culverts where the streams are in this representation. And again, these streamlines are replicating the DNR 24K or the current NHD. So we're not going beyond that for a level of detail for intermittent streams. Here again, we have another example where the culverts are yellow. In the center of the screen, we can see there's a kind of a glob of yellow. That means that, if we were to zoom in here, there'd be either a double or a triple culvert. You're going through that line. And then here we have an example of the old versus the new. So this whitish yellow line here coming through at a diagonal, that is the current 24K or NHD hydrography layer. Now, if you were to go out and talk to the landowners in this area, the farm field owners, everything, they know very well that the stream doesn't flow there. And we can see in this LiDAR DEM that there's not a culvert here or down here, where the streamline is crossing those roads. Really, the true flow path is to the north here, and where it cuts across through a culvert and then follows the ditch, and then it comes back down through another culvert. So, if there were any management strategies applied to this streamline, this hydrography, if you were to use the old hydrography and try to implement a riparian area or some sort of blanket management strategy, you'd have some pretty upset landowners in the area saying like, well, hey, this stream isn't even on my property. That's on the northeast side of this intersection, not on the southeast. So it really goes to prove that the current inventory, it just needs to be maintained every few years or every decade or so. It needs to be updated so we can have the best management strategies out there. Now, how do you select your thresholds for determining a river? This example here, these are all of the depressions along the landscape, and not every one of these lines is a stream or a river. And so, when it rains in a heavy, 100-year event or something, yes, there may be overland flow in all of these depressions along the landscape, but they are not intermittent or perennial streams by any means. And so you need to set your thresholds accordingly and maybe play around with that depending on the terrain of your project area to really derive the most accurate network that replicates the need for your project. And again, the need for the project that I'm describing here would be to replicate the 24K or the NHD inventories. So again, that's just what I said here. We're just trying to replicate these lines. We're not trying to go to the detail and figure out every small depression along the landscape, every rill or anything. We're just trying to replicate these lines, make these more encompassing of the landscape. And so we can do that, and we can go a little bit beyond. But like I said, you make adjustments to your contributing area thresholds to derive various details across the landscape. And now, why is this important to update these things? Well, a stream changes. If you go out into a natural area where there isn't any buildup, and if you do a time lapse on the imagery from over that natural area, you will see that the meander bends change over time. Maybe at once every decade, there's a significant water event. And because these dynamic features are important to us, and we live relatively close by to a lot of streams and rivers, we would like to have these updated on a more frequent basis than just once every 50 or 100 years. ideally, it would be nice to see these updated maybe every time there's a new LiDAR collect, or maybe once a decade or so. And so to prove that point, here we have some imagery from the North Shore of Minnesota. This is an image from 1991. That we see a stream flowing through here. We have some braiding, some point bars. And then a decade later, 12 years later, we see that, there's some significant change. There's increased point bars, some energy has flowed down this river and created new meander bends, farther downstream, more braiding. If we go 5 years into the future, there's not too much change, but then another 5 years, and we see that there's, this point bar is extended and the river has changed again downstream. So just in these few images, we've seen at least once every decade that there's been a significant event, significant enough to change the watercourse hydrography. Significant enough that it should be updated for land managers to utilize. And so here we can see the current stream inventory, the old inventory, and what the new LiDAR derived hydrography would resemble. And why are we talking about hydrography and for best management practices and everything? Well, oftentimes it's much more cost effective to manage your hydrology or your hydrography products from the ground up, and then you can manage any other sort of biota on top of that much more easily. If you're trying to assess where there's riparian habitat, or if you're a herpetologist and you're interested in certain frogs breeding in vernal pools, or you're trying to figure out where there's some duck habitat, there's just a base set of products that for hydrography and water bodies that you want to put into your models before you get up to managing the biology. Oops. And so once you have those streamlines, right, you can do many other things downstream of having those products. So you can create management boundaries for habitat or a riparian area. You can do closed depression landscape or mapping across the landscape. You can also model the erosion and deposition that happens along those river corridors. But right, it's all about the that river corridor being the most accurate that we can have at that point in time. And so just a couple quick examples here. This is a headwater watershed up in the North Woods of Minnesota. And here we have a LiDAR-derived stream flowing through. This is a nape image. So it's collected this image is collected in the late summer here. So here we can see some aspens, some upland aspen stands. They're yellow, but then we also can see some black spruce wetlands and even some tamaracks changing yellow in these wetlands. We also can see possibly some beaver dams with some water behind them to the side of these areas. And so we have the stream corridor. What can we do beyond that? Well, we could create a topographic riparian area around this streamline. So here we have some polygons that incorporate, the black spruce swamps and the tamarack swamps, and then all these beaver dam locations moving upstream. So that, there's many different downstream products that you can create once you have that hydrography in your back pocket. And so looking towards the future, NEXRAD and the USGS are currently establishing a 3D hydrology or hydrography program. So instead of 3 depth for the elevation program, they're calling it 3D HP for hydrography program. So they have a common goal to standardize that NHD or the 24K streamlines to align not only vertically and horizontally, but temporally, with that 3D LiDAR elevation program that's coming in. So that kind of goes towards that notice, or every time we get a new LiDAR data set for an area, it's advantageous to update the hydrography for the area as well. And so currently USGS and NEXRAD are exploring options to have future funding similar to the 3DOT program for updating hydrography. So really excited to see what comes out of this in the next couple years or so. But we, I myself as a water enthusiast, water scientist, I'm really excited to see these products being updated here in the near future. And if you have any questions, I'd be happy to field them now.
That was great, Tyler. Thanks for your presentation. If you have any questions, you can put them up in the Q&A or in the chat. I just have to say your comparisons with the historic data to current flow paths is quite astonishing. It's good to know too that there's a national push for these corrections. That's what it sounds like anyway, that the USGS, through the guidance of NEXRAD and so on, they'll be able to fund and update these products. Is that how I should interpret that?
Yeah, I think the goal would be to have funding opportunities to support project partners to update. So it may be a county or the state, would like to update those products. Then the county or like a soil water conservation district could apply for a grant to the USGS to possibly go in, at a 50-50 contribution percentage to get those products in-house. So the USGS wouldn't be fully funding those. It would be a partnership, like the current LIDAR 3DOT program works.
Sure, and then those products would be available, of course, to the county, and then it would be incorporated into a larger national data set or updating that national data set.
Correct.
Great.
Yep.
What do you think the biggest challenges or obstacles are for updating the stream corridors? Maybe in-house expertise or money, or do you see anything as a great obstacle?
Yeah, I mean, the biggest challenge is getting that input data, getting that culvert data and the LIDAR data. So once, if a county or an entity already has updated LIDAR data, well, then they're miles ahead of most of the folks out there. But then utilizing imagery sources and the LIDAR sources to create a culvert inventory, really, that takes a lot of time. Sometimes there's boots on the ground actually inventorying these things. Sometimes it's using street view or high resolution imagery gathered just specifically for this purpose. But it really takes a lot of multiple products to come together to get those inventories to move forward with the processing. So it's kind of a waterfall approach, right? You have to have some dominoes falling before you can get to this highly detailed level for the hydrography. So that's our main obstacle. It seems like a lot of people are interested, but they need to set up these other projects beforehand before we can get to the updated hydrography.
Yeah, thanks for that answer. Yeah, culverts, and just seeing the example that you have, there's so many of them, and tracking and updating and having that data set is an imperative piece of this model. And yeah, I can imagine that would be a big push for for a county that hasn't started.
Correct. But if there are counties out there that are ahead of the curve, they have recent LIDAR and maybe a high resolution imagery data set from the last couple of years, then they're ready. They can get the culvert inventory completed and then start on modeling. But it just, again, it takes a lot of coordination between multiple entities, multiple project partners to really get focused on similar goals to work towards together. And I really appreciate everybody for stopping by and And viewing the slides, some of the names on the attendee list I see are familiar, and they may recognize a few of these project areas. So thanks for joining.
Thanks so much, Tyler. Thanks for joining us, everyone. Have a great conference.